In section 4.4, we're going to talk about some different theorems about the zeros of polynomial functions. And we've already used quite a few back in section 4.3. We talked about the link between intercepts and zeros and factors and things like that. So we're just going to keep talking about some of those similar things. In section 4.4, one of the first things they start talking about is if you have a polynomial with real coefficients, so remember our basic setup for the polynomial was a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way down to a sub 1 x and a sub 0. So what we're saying is the a's here, those are our coefficients. Those have to be real numbers. And if they were not real, then they would be complex, which means they could have the letter I in them, which means square root of negative 1. So not complex, which means no i's. So if this is true, then we can factor this polynomial into n linear factors. But within those factors, there might be complex numbers, and it's not necessarily going to be unique factors where there's n different factors. Some of those factors could be repeated, just like when we talked about multiplicities a couple sections ago. It could be that x minus 1 in the factorization is cubed, which means x minus 1 works 3 times, or it's needed 3 times to help with the factorization. So not necessarily unique, and they could include complex numbers. So one of the things we said in one of the last couple sections is that, so we want to recall, if x equals a is a 0, then x minus a is a factor for whatever polynomial we happen to be working with. So if we know something is 0, then we can use that information to create a factor. And if we know all of the zeros for a polynomial, then we could potentially write out all of the factors of the polynomial. Even if it's something that we don't traditionally know how to factor by hand, we can get the same information just by looking at zeros, and also x-intercepts. We had a link for that as well, which we'll talk about again here in a couple minutes. So there's an example I want to show you where we are told all of the zeros for a polynomial, and we're asked to figure out what that polynomial is. So one more thing I want to tell you real quick is if all of the a's are real numbers, and more specifically, if all of our a's are rational numbers, which means they can be written as fractions. And some numbers that can't be written as fractions are numbers such as pi or square root of 2, things like that. Those cannot be written as fractions. It's not possible. Then complex and irrational zeros will always come in conjugate pairs. If you remember back to the beginning of chapter 3, when we learned about complex numbers, when we multiplied conjugates together with complex numbers, the result no longer had an I in it anymore. So if our polynomial has no I's in it, so all of those coefficients are real numbers or even rational numbers, then anytime we have a complex or irrational zero, they've got to come in a conjugate pair so that when they get multiplied back out, the irrational pieces cancel away or the complex pieces cancel away. So for example, if 2 plus 3i is a zero of a real valued polynomial, without anybody even telling us, we just have to know that automatically 2 minus 3i is also going to be a zero. Because these two are conjugates. And what makes them conjugates is that the sign in front of the imaginary term is different, but everything else is exactly the same. If 3 minus root 5 is a zero of a rational valued polynomial, then 3 plus root 5 is also a zero. So this is an irrational number. It's got square root 5, which does not simplify. And the only way to get rid of all those radicals when we multiply all these factors back out to create the polynomial is that its conjugate pair is also there, so that when they get multiplied together, the result ends up with no irrational parts to it. Oops. So if I were to give you the zeros for a polynomial, then we could write out all the factors of the polynomial. And if we can write out all the factors of the polynomial, then we could multiply them out and actually figure out what this exact polynomial is. So we want to find a polynomial whose zeros, and let me say a real valued polynomial, because if there's any complex, they have to have their conjugate there. So we want to find a real valued polynomial whose zeros are x equals 3, negative 2, 5 plus I, and 5 minus I. And each have a multiplicity of 1. And what that means is when I write the factor, there's only going to be one of them. If one of these zeros had a multiplicity of 2, then when I wrote the factor, I would put a squared on it. Or a multiplicity of 3, I would write the factor and put a cubed on it. So I'll do another example in just a minute where we have a different multiplicity. So we've got those 4 zeros, and according to that rule I gave you right at the beginning of this section, that means that this polynomial can be written as x minus 3, x minus negative 2, which will be x plus 2. And be really careful with the complex zeros because it's x minus your 0, and it has 2 terms. So it's x minus 5 plus I and x minus 5 minus I. And before I multiply out, I'm going to have to go ahead and distribute. So we get x minus 3, x plus 2, x minus 5 minus I, and x minus 5 plus I. And we're not done until this gets all FOILed out. So I'm going to start with these two because these tend to be the trickiest. Anytime you have to multiply out very large polynomials, the rectangle method could be very helpful. And the rectangle method helps you keep all of your different multiplications nice and organized and make sure that you've done all of them. So what I'm going to do is I'm going to write one of these spaced out on the top, and I'm going to write the other one spaced out on the side. And there are 3 terms in the top, 3 terms on the side, which means we have a total of 9 multiplications to do. So in each of these boxes, I'm going to look at the term that's on top and the term that's on the left and multiply them together. And once I've filled in all the boxes, I know I've done all the multiplication required. And I can add all 9 of these pieces together, and hopefully a lot of them will combine and simplify. So this is going to be x squared minus 5x minus xi. And then minus 5x plus 25 plus 5i. And then plus xi minus 5i and minus I squared. But remember, I squared equals negative 1, back from chapter 3. So I'm going to have negative I squared, which means I'm really going to have a plus 1. And there are several things in here that will cancel and simplify. I've got a minus xi and a plus xi. I've got a minus 5i and a plus 5i. So all 4 of the pieces that still had i's in them canceled away. And I'm going to pull together everything I have left over. So I've got x squared, takes care of that. I've got minus 10x if I put those together. And I've got plus 26 if I put those together. So that's just my last 2 pieces multiplied together. We would also need, what I would do is FOIL those out as well. And that's my other quadratic. And that one's going to be x squared plus 2x and minus 3x is just going to make a minus x. And then negative 3 times 2 is, sorry, I'm going off the screen here, minus 6. So the last step now would be to multiply these 2 polynomials out. And I'm going to do another box method just like this one. So we've got x squared minus 10x plus 26. And I always bring the signs with me just to be safe. And my other one was x squared minus x minus 6. And there's 3 terms times 3 terms. I'm going to get a total of 9 multiplications that I need to do. And some of them will combine in the long run. So to fill in each of those boxes, look at the term at the top and the term on the left. We get x to the 4th minus 10x cubed plus 26x squared minus x cubed plus 10x squared minus 26x minus 6x squared plus 60x, because they're both negative. And then 26 times 6 is going to be minus 156. And I need to put all that stuff together for my final answer, and there are some like terms here. So there's only one x to the 4th piece. I've got 2 x cubed pieces, negative 10 and negative 1 of them. That makes negative 11 of them. And then I've got 3x squared pieces. 26 and 10 is 36, and then minus 6 is just 30 x squareds. And then 2 linear pieces, a positive 60 and a negative 26 makes a positive 34x, and then just 1 constant. And that would be our final answer for the polynomial that has those 4 zeros that were given to us. So this box method works really well and keep everything nice and organized.